Okay, in this video we're going to discuss the variance of a combination of random variables where x and y are independent random variables and c is a real number. We're going to look at the variance of c times x plus y, so some number times x plus y. And note, this is the same kind of thing we looked at for linearity, but we'll find that variance doesn't have linearity. Variance doesn't act linearly. It does distribute over sums, but constants don't exactly pull through. Something happens to them when they pull through, and we'll see exactly what that is. Okay, so we're looking for the variance of this random variable, cx plus y, assuming x and y are independent, discrete random variables. Okay, so the variance of cx plus y I'm going to denote by sigma squared with a subscript of cx plus y. And that, as always, is the expectation of the value of the random variable, and we're thinking of this whole thing, the two terms, as one random variable minus the expectation of that random variable squared. Okay. And in all of the examples where we've looked at variance of a binomial random variable, or a Poisson random variable, or a Bernoulli random variable, we've went straight to the sum, but we're not going to do that here. We're going to work straight with algebra and linearity of expectation. Okay, so first thing we're going to do is apply linearity of expectation, and so from the previous section we saw that the expectation of cx plus y is c times the expectation of x plus the expectation of y, but I got this minus sign out here, so that's going to give me a minus expectation of y. And I've got this whole thing squared. Okay, now I'm going to pair the x's together and factor out that c to get a c times an x minus the expectation of x. Okay, so that was this term and that term. And then I also have a y minus the expectation of y. I'm going to go ahead and put that in parentheses, even though I don't have to, and that's to emphasize how this next step is going to be carried out. Now I have two terms here, and these two terms I'm going to think of this as a squared binomial in these two terms. And actually that second term, that's misleading, doesn't extend that far. It only extends to that middle parenthesis there. And it's the sum that is squared. Okay, it's not just the second term, it's the sum. It's both of them that are squared. So when you square a sum like this, let's go back to a white pen, what do we have? We have the first term squared, so that's c times x minus expectation of x squared, plus 2 times the product of the two terms, so that would be plus 2c x minus expectation of x times the second term, y minus expectation of y, plus y minus expectation of y squared. And since we distributed out that squared, we don't need this outer set of parentheses anymore. We do need the brackets to signify that we're taking the expectation of the entire thing. Okay, now again, expectation acts linearly. So I am going to distribute the expectation over these three terms. Alright, and distributing the expectation over these three terms, first of all I'll distribute over this first term, and the c squared comes out, because that's a constant. And I'm going to give myself a little bit more space here. So that'll be c squared times the expectation of x minus expectation of x squared. Plus, again, this constant will come out and we'll get 2 times c times the expectation of x minus expectation of x, y minus expectation of y. And this is messy no matter how you write it down. In the past we've been using mu's. I chose not to use mu here because we have two different random variables floating around. So they'd have to have subscripts, and that would be messy as well. And then finally the expectation will distribute to this third term, and we'll have the expectation of y minus the expectation of y. Let's see, I guess it's that whole thing squared. Sorry for the messiness there. It looks like this over here, except for x's are replaced with y's. Okay, so what do we have? Well, this part is c squared times the variance of x. I'll call that sigma squared sub x. This part is the variance of y. Right? That's what it means to be the variance of y. It's the expectation of the variable minus the expectation of the variable squared. The expectation of y minus its mean squared. Okay? And what we're going to find is that this whole thing ends up being 0. But we need to work a little bit to get that. So what I'm going to do is erase all this stuff up here and give me room to show that this expression, this term, ends up being 0. Okay, so we have 2 times c. Now, I'm going to go ahead and distribute out what's inside these brackets here. I got x times y, so that's xy, and then I have x times the expectation of y with a negative sign, so that's minus x expectation of y, and then I have a negative sign, expectation of x times y, so that's minus expectation of x times y, and then a minus and a minus make a plus, and I have expectation of x, expectation of y. Now the expectation of a random variable, like expectation of x or expectation of y, that's a constant. Okay, it's not itself a random variable. For example, the expectation of a Bernoulli random variable is p. A p is a number, it's not a random variable. So this is just a constant, this is just a constant, and this is just a constant. Right? Now we can apply linearity to this expectation and break it up, so we get 2c times the expectation of xy minus 2c. Remember, expectation of y is a constant, so I'm going to pull that out, and I'm left with the expectation of x. Similarly, over here, I'll pull out the expectation of x, and I'm left with expectation of y, so that'll be minus 2c expectation of x, expectation of y. And then this is just a constant times a constant, so it is a constant. The expectation of a constant is that constant. So we'll have plus 2c expectation of x, sorry to have to cram this in here, expectation of y. And I apologize, I don't see the borders of my screen. Well, I see the borders of my screen. I don't see the borders of the recording. The recording doesn't quite go to the end of the screen, so I might be cutting something off, especially down here. I apologize for that. Okay. Well, we've got a little bit of something to be optimistic about here. These two are the same. Okay, so this and this will cancel out, and we're left with these two terms. Now, independence, right? That was one of the suppositions for this theorem. And that is needed. For the linearity of two random variables, you do not need independence, but to be able to compute the variance of a constant times one random variable plus another, you do need independence. And the reason you need independence in this calculation is that independence gives the expectation of xy is the expectation of x times the expectation of y. And that's a homework assignment. Though I think it might only be assigned to the graduate students. So since we have that, then this expression is 2c expectation of x, expectation of y, and I switched to parentheses just because I'm used to doing that when I have a less complicated expression inside of there, minus 2c expectation of y, expectation of x. Okay, remember those two terms canceled. So we're left with, again, two identical terms, and that's just 0. And we see if this term is 0, and that's sigma squared of a constant times a random variable x plus a random variable y is that constant squared times the variance of x plus the variance of y. So we almost have linearity of the variance. Right? If I multiply a constant by a random variable, add another one, take the variance, I still get the variance of one random variable plus a variance of another random variable, and there's a c that comes out, but the c actually ends up being squared. And the reason that the c ends up being squared is that when we take the variance of something, for example, here's the variance of x, we square these values. Okay, so that squared caused the c to be squared. Okay, so there is the proof of this theorem, and this will actually end up being important when we get to the central limit theorem. And the central limit theorem applies when we want to take multiple observations and average them or combine them in some other ways. Usually, if you make several measurements, you average the result. Well, to be able to describe what kind of a distribution that average will follow, we need to be able to work with combinations of random variables like this.